Here are some quick notes on simple atmospheres to accompany Chapter 2 of To Build a Star. So for a simple atmosphere, let's just consider a floating fluid element. So this is how we're going to derive the equation of hydrostatic equilibrium, which essentially determines the structure of any static fluid. So we have a fluid element here. It has some weight, that's mg. There's forces on all sides of this fluid element, okay, from just the surrounding pressure of the surrounding fluid, and there's also the downward force of gravity. So what we need to do, this is a static fluid element, it's not accelerating upward, downward, left, or right, so that means that F equals ma equals 0, right? There is 0 acceleration on this fluid element if it is static, if it's not accelerating up or down. So the net force, the sum of the forces, needs to be 0. So what forces do we have? We have downward gravity, we have pressure inward from all sides. The non-vertical pressure forces are all going to cancel, so I didn't even bother drawing them because it'd be a pain, but you know, the fluid on the left of the box is not any different than the fluid on the right. The areas are the same, and so those pressures are just obviously going to cancel those forces. But for the vertical, we have that the upward pressure, right, is going to be equal to the downward pressure plus the force of gravity. So we have these two forces down, those oppose that one force up, and you all recall that a pressure is a force over an area, so that means your pressure force is equal to the pressure itself times the area of the fluid element. Okay, so then we're just continuing with this equation here that the upward pressure is equal to the sum of the downward pressures, but we're going to move the pressure forces to be on the same side. So then we have the area of the top or bottom of the fluid element times the difference between the pressures. That's just going to be equal to the force of gravity, which, as you all know, is mg, right? That's the local gravitational acceleration, and that's the mass of the fluid element. We don't want to be worrying about how big our fluid element is, so we'd rather worry about a sort of local macroscopic quantity like a density. So mass is nothing other than density times volume. And of course, the density is nothing other than the height of the fluid element, or sorry, the volume rather is nothing other than the height of the fluid element times its area. Why do we do that? Because our areas can cancel. And then we can do the usual physicist thing of taking a difference, dividing it by another difference, and saying, that's a derivative. And so then the derivative of the pressure versus height is equal to the density times little g here. And then we're going to write this actually as a derivative. dp dr is minus rho g, and the local gravity, this can change depending on the radius of your fluid element, right? So the force of gravity is very strong on the surface of the Earth, for instance. If you go up out to the moon, the force of gravity from the Earth is not strong. So obviously that has to be dependent on the radius. So this is your equation for hydrostatic equilibrium, and as you can see, deriving it's pretty straightforward, and so that's all something that you should be able to do. Now, an equation of state, this relates to pressure of density. You guys probably all remember PV is equal to nRT. Well, probably a better way to write this is that pressure times volume is equal to the number of atoms or molecules, really, times the Boltzmann constant times the temperature. We can then move the volume over to the other side, so we just have pressure related to something else. Get this equation here. Again, we'd rather not be worrying about how many actual molecules we're talking about, so we can just change this into a macroscopic quantity, the density, divided by the average mass of a molecule within the fluid. So if your fluid were all made out of a single atom, for instance oxygen, you just have the mass of oxygen here times the mass of times the atomic mass unit. However, this is the mean molecular weight, basically the average molecular weight. Mu is what you'd use instead if you have a fluid with multiple components to it. So then finally you get that basically, the pressure is equal to the density times temperature times some constant, or you can change it here and have the density in terms of the pressure. Okay, so now finally we can take this equation. We have the density as a function of the pressure. We can substitute that into the hydrostatic equilibrium equation, and then we get an equation relating the derivative of the pressure to the pressure itself. You can solve that. So the way to do that is to realize that this is a homogeneous linear first-order differential equation. You basically get pressure on both sides, radius on both sides, and you integrate integrate the pressure, integrate the radius. You go consult a math methods textbook and it'll refresh your memory. And what you get is this barometric formula, where you see that the pressure as a function of the height, or really the radius from the Earth, is equal to some reference pressure, and it decreases exponentially. And the scale constant for that decrease is known as the pressure scale height, and right, that's just going to be related to these constants here. Good of an approximation is that isothermal atmosphere. So back in that equation, we just had a fixed temperature. Well, you can see it's not so bad. So this is for the Earth. You see that the temperature is a function of height. It varies a decent amount, but you're really only talking between like 200 and 300 Kelvin, so that's not that big of a change. And the pressure does fall off roughly exponentially, just as we said it would in our formula. So at least for, atmosphere, the atmosphere up to like where planes fly, the barometric formula is definitely good, and life maybe gets a little more complicated as you go to higher atmospheres. Okay, so just to finish up, let's discuss the atmosphere composition. So we had this mu, this mean molecular weight. How would you calculate that? Well, you basically just need to know what's the composition of your atmosphere. So this would be the sum of the weights, or the mass number of each molecule, times the percentage of that molecule in the atmosphere, so by number. So for instance, the Earth's atmosphere by number is 78% nitrogen, and then most of the remainder is oxygen. You have a little bit of argon and then some CO2, and you could pretty much ignore everything else. So if you want to calculate the mean molecular weight for the Earth, you just take into account those 1, 2, 3, 4 components, and that's pretty much close enough. And if you really want to get fancy, you can go down to this detail here. If you're talking about different planets in the solar system, their atmospheres are actually quite different. So Earth, we're mostly nitrogen and some oxygen, a few remainders here. You go to Venus and Mars, you're actually mostly carbon dioxide. And then there's trace elements of nitrogen and argon. When you go to the gas giant planets, you see that you're actually mostly hydrogen, and then the remainder is mostly helium. And the way that you can understand this is actually kind of interesting. It's basically just physics 1. You can calculate the escape velocity for your planet just based on the mass of the planet, based on its compactness. So you can calculate the escape velocity. Then if you know the temperature of that object, then you can calculate the average kinetic energy of a molecule just based on the Maxwell-Boltzmann distribution. And so the higher temperature you have, then your molecules are going to have a higher average velocity, so they're going to be able to escape heavier objects. And so then when you think about that, you see that basically the escape, whether or not you can maintain a gas in your atmosphere, it depends diagonally along this plot. Okay, so basically the moon can kind of barely hold on to some xenon. You have some moons of Jupiter, for instance, can barely hold on to carbon dioxide and some oxygen. The Earth itself is interestingly barely holding on to water vapor, but doesn't actually keep helium or hydrogen. So that's why you just don't have it in the atmosphere other than being trapped in the water. And then the gas giants, they can hold on to all of the helium and most of the hydrogen, and that's why you see their atmosphere is dominated by that. One interesting thing to note that's totally unrelated to this class is you might wonder, well, wait a second, if the helium escapes the Earth, where in the heck do we get helium gas from, right? For your party balloons. And that comes from natural gas extraction and fracking, so from the Earth. And why is that gas trapped in the Earth? It's because the center of the Earth has a lot of uranium in it and transuranic elements. Those undergo alpha decay, and alpha particles are just helium nuclei. And so your party balloons actually come from radioactive decay in the Earth, which is kind of a fun note. Okay, well, this class is about stars. What are star atmospheres like? Let's take a look at the sun. So what's plotted here is a plot I made of the proto-solar abundances. Whoops, I wrote I mean proto-solar abundances, calculated from the data in this paper. So this is the composition of the sun at the time it was formed. You're looking at a log scale here versus the atomic number. And you can see that you're mostly hydrogen and helium, just like our gas giant planets. If you want to get fancy, you should maybe take into account carbon, nitrogen, oxygen, these CNO elements, which are at a factor of 1,000 less in the fraction of the composition. And you really get some trace elements and all the way down to uranium, where you have 9 zeros. And then, so it's 10 to the minus 10%. So that's all just to say these are typical compositions, and this is how you'd calculate that mean molecular weight to go put into your barometric formula to calculate the pressure of an atmosphere. And that is it for these quick notes on simple atmospheres.